remember to record this video. Okay, so I'm recording this. If you guys need to consult it later, or for the folks who did not make it. All I want to do today is just make sure that we're all on the same page, so to speak, about rotation so far. So if you guys have not noticed, this unit is basically all of our other units combined into one. Everything that we've been doing so far has been for a translational motion, and I hope you guys understand what I mean by that, like motion along a plane, right? Motion in a straight line or a curved path along a plane. What we're doing here is we are using all the concepts that we have so far, and let's talk about what they are. Kinematics, forces, dynamics and statics, energy and momentum. Those have been our 4 units so far in this course. And this unit that we're in now, Unit 5 rotation, is all about taking all of those concepts and reapplying them to analyze the physics of objects that are rotating, that are capable of spinning. So far we have looked at the kinematics of that. Hopefully you guys are keeping all of those variables straight in your brains and how they're related to each other. You know that we have angular velocity, angular or rotational acceleration. If we think about a rotating object as composed of a bunch of point particles, or if we focus on one point on the rotating object, you know that that point is moving in a circle, and you guys know that for anything to move in a circle, there has to be an acceleration tangent to the path, so we call that a centripetal acceleration. So we also have that going on. And then we know that every instant in time, those point particles on the rotating object also have a tangential velocity. If they're accelerating, they have a tangential acceleration. So we have all these velocities and accelerations, and I've tried really hard to just help you guys try to keep those straight and those relationships straight in your head. So does anyone have any questions about that, about how those variables are related to each other? I really tried to go over it in all the videos that we've had so far. Y'all feeling okay about that? And then of course we have this rotational equivalent to mass. It's called rotational inertia. And once again, really hoping that you guys are getting kind of the conceptual hang of that. This pin, for example, if I want to start rotating it, I'm going to have to apply something called a torque. We're going to talk about that. But how much force I need to set it to rotate with a certain angular acceleration is going to depend on where the axis of rotation is. So that AOR, that axis of rotation, is always going to be, in all these problems, it's always going to be the first thing you define. Am I trying to rotate it about this end? Am I trying to get it to rotate with this end fixed, and this is the axis of rotation? Am I trying to get it to rotate about the middle, somewhere in between? And you guys know that the inertia, the tendency of an object to resist rotational motion, rotational inertia, it does not just depend on the mass of the object. Mass is inertia translationally. You know, if I'm just going to push it and see how it accelerates in a line, that acceleration is going to be resisted just purely by the mass of the thing. That's translational inertia, mass. Rotational inertia, though, you guys hopefully know it depends on 2 things. Someone want to raise their hand and tell me what 2 things rotational inertia depends on? I'll give you a big hint. Mass is one of them. Ooh, I'm going to call on somebody. Mr. Davis, tell me what 2 things rotational inertia depends on.
The force and the radius.
Okay, so you're close there. I'll take it. I suppose it depends on mass, the mass of the object, and how the mass is distributed. You said radius, so that's like the r in rotational inertia, right? Rotational inertia is the integral of r squared dm. That r in that equation is how far away the little mass is from the axis of rotation. So it does depend on the mass. And then I would say the second thing that rotational inertia depends on is how the mass is distributed on the object away from the axis of rotation, okay? For example, this object here, I think I mentioned this in a video, we probably talked about it before, but if the axis of rotation is the end, and I try to start swinging the object around like this, I have more mass that is farther away from the axis of rotation. So the rotational inertia will be larger. It's actually more difficult for me to cause this thing to swing around about its end because there's more mass located farther, the entire length of the thing, farther from the axis of rotation. However, if I try to swing it around the middle, and this is the axis of rotation, now I have less mass that's closer to the axis of rotation. The R value would be smaller, if that makes sense. So if we do that I calculation, we'll get a smaller value. So conceptually, you guys need to understand that rotational inertia, where that word inertia means the tendency of an object to resist changes in motion. So we're talking about resistance to change rotation, rotational motion. The rotational inertia depends on how the mass is distributed away from the axis of rotation. So the first thing we have to do is define the axis of rotation, right? Typically, we like to, let me get the whiteboard up real quick. Sorry, y'all, 1 second. Hi, Mr. Nandy. Okay, you guys can see the whiteboard, right? Oh wait, I just saw Mr. Coleman ask me a question. How is the axis of rotation related to the center of mass? Your objects tend to naturally rotate about axes that go through their center of masses. That's a great question, Mr. Coleman. Yes, so an object will tend to rotate about its center. That's true. So imagine, this pin floating in space and something like bumps it right here or something like that, then it is going to tend to rotate about its center. That's very true. If I want to change that, I'm going to have to, hold a different part of the object fixed and immobile. So if this pin is just floating in space and it gets bumped into by an object away from its center, then that's going to supply a torque to start the thing rotating about its center. If I want it to rotate about an end, I'm going to have to somehow fix that end and apply my torque. So yeah, good question, Mr. Coleman. Okay, you guys can see the whiteboard, yes? Anybody? Just want to make sure you guys are seeing what I'm seeing. Okay, I'm getting a thumbs up from Mr. Pribidesai, so I'm assuming that is good. So I just wanted to just real quick make sure that we're all on the same page about this. This is what we've been talking about. That's the calculus definition of rotational inertia. Now, of course, you know that we have a non-calculus definition. In other words, if we just had like a collection of point particles, and that collection of point particles maybe are connected by like a very, very, very light, thin rod that is so light we don't care about the mass of it, then and maybe here's the axis of rotation of this collection of point particles, then we don't need to integrate, right? We can just use a summation idea where we would take the mass of each point particle, multiply it by the distance to the axis of rotation squared, and then add all those up. And that would give me the I value that way. So keep that in mind. Okay. So typically what we like to do, and we've done this many, many times, we did this before spring break. I just want to remind you guys about it. So typically we like to first look at an object rotating about its center of mass and find the I value for that using calculus. But what if we wanted to find the I value for an object not rotating about its center of mass, but maybe rotating about a different point? Um, Maybe I wanted to find the I value like right here, which is if this here is the center of mass of the object, maybe I'm halfway between the end and the center of mass now. So if this whole thing had a length L, this would be a distance of L over 4 right here. Anyone know an equation or an idea that can help me find this new I value once I've shifted the axis of rotation away over to the left now? This is my axis of rotation right here. Let's see, Brandon New, Mr. New, any thoughts about how I could find now the new I value, the new rotational inertia about this new axis?
I have no idea what you would do.
Okay. You want to phone a friend, my guy?
No.
Okay. Mr. Prabhudas, do you know?
It's that one equation that I forgot.
Okay, you're right. It is an equation. Yeah, so if you guys have been watching the videos and taking notes, I've mentioned this several times. I don't know if we've talked about it yet. Maybe we have. But I do want to make sure that everyone knows this. It's called the parallel axis theorem. You guys need to know this, memorize it because it's not on the AP equation sheet, and I can guarantee that you're going to be tested over it. The parallel axis theorem basically says that, hey, if we can calculate the I value about the center of mass, which is easy, that's always easy to do. Every calculation that we've done using the calculus definition has been about the center when the axis of rotation is lined up with the center of mass. If we know the I value about the center of mass and we add to it this little chunk, md squared, then we will get the new I value. Maybe I can call it I prime, or the I value about a new axis. So can someone tell me what that D represents in the equation? Mr. Coleman, do you know? Mr. Coleman. Miss Laird, do you know? What does this D represent?
Is it the distance the new axis of rotation is away from the center of mass?
I could not have said it better myself, my friend. That is exactly correct. So in this example, we could calculate the I value for a rod about its center. I don't remember what that is. I think it ends up being like 1/12 or something. 1/12 mr squared. Anyway, we can calculate the I value about the center of mass. And then using the parallel axis theorem, we can find any new I value about any new axis of rotation by just adding this term where m is the mass of the whole thing and d is the distance that we have shifted the axis of rotation. So in this example, I have shifted the axis of rotation to the left by a value of L over 4, right? The whole length divided by 4. So my d in this example would be L over 4, and I would square that and plug it in here, okay? And then of course I would add those together and get my new I value. So you guys must know this parallel axis theorem, you must memorize it. We're gonna practice with this, so it should become second nature to you guys, but I just wanna make sure that we're all on the same page about it. So hopefully that helps. Yeah, so there's things to keep in mind. All right. Okay, so let's talk real quick about torque. Torque has this abbreviation, tau. I always make my little tau curl go the wrong way. I believe it curls around this way. And the mathematical definition of that is R cross F. So first of all, you see here that we have, this is not just plain old multiplication, right? I'm multiplying two vectors and getting a vector result. This is called a cross product. So anyone, any brave soul out there want to try to explain to me how a cross product works and why it's important? Like, what does it think about? What are we worried about when we take the cross product of two vectors? Miss Brianna Scott, do you have any thoughts about that? What is the meaning of a cross product?
They're perpendicular to each other, and like you're just concerned about the perpendicular force.
Excellent. Yeah, very good. Your audio cut out there a little bit, but I think I got the gist of what you said. So Ms. Scott said that you're worried about the component of one lies perpendicular to the other. In the lecture video, I contrasted this to the dot product. Remember the dot product, we're worried about the component of the two vectors that lie along each other, how one vector lies along another one. So for example, if here's two vectors, maybe I'll call this one A and this one B or something like that. Then if I took the dot product, and here's the angle between them, notice that whenever we do, I tried to emphasize this as well, whenever we do multiplication, vector multiplication, either dot products or cross products, we like to draw the two vectors tail to tail, and that will give us theta, where theta is the angle between them. If I am taking the dot product, A dot B, then that collapses down into AB cosine theta, because I'm basically asking, like, how does B get amplified by A? That's one way of thinking about a dot product. How much of A lies along B? And you can see here that if I break A down into components, this is a component right here. I don't know if I can change the color. Oh well. This is the component right here of A that lies along B. And what would that value be equal to right there? It would be equal to A cosine theta. So it's like I'm taking one vector, the B vector, and amplifying it by the value of the other vector, the component of the other vector that lies in that same direction. And the answer to a dot product is not a vector, it's a scalar. So sometimes we call this scalar multiplication or a scalar product. Let's see, Mr. Bilac, can you give me an example of a concept in this class that utilizes the dot product?
Does the one second. Work, or is it work?
Yeah, it is. Excellent. Great job. Yeah, work. Work is defined in its general calculus definition as F dot dx or dr, I think I sometimes say, where this is a vector, force vector, and this is a displacement vector. And we integrate all the forces along the little displacements as a dot product. And that gives us a scalar change in energy. You know, the energy is not a vector, it's a scalar. So that is an example of a dot product. Excellent. Okay, a cross product, if I were to do, here's vector A, here's vector B, here's the angle between them. If I were to do A cross B, that collapses down into AB sine theta. And A sine theta would give me the component of A that lies perpendicular to B. It would give me this right here. Like, how much does A go towards, you can almost think about it like this. Last time we're looking at how much does A amplify B, how much does it agree with B? Now we're asking the question, how much does vector A lie perpendicular to, like, you know, imagine that you're pushing B with A or something. How is B going to end up changing its direction from that push? That's the perpendicular component that we're worried about. So that would, of course, be, geometrically speaking, this leg here would be A sine theta. So dot products, we use cosine, cross products, we use sine. This angle theta is always going to be the angle between the two vectors when you draw them tail to tail. And it's important to note now that your result here is a vector. This is vector multiplication. Sometimes we call the cross product a vector product. So let's do an example of the cross product that we do in this course, which is torque. So once again, torque is equal to R cross F. And I think in the lecture video, I used an example of a door or something. So let's say this is the top view of a door. Let's say this is the axis of rotation. So these are like the hinges over here. And let's say that you are pushing the door. Oh, I don't know. You push it over here this way. Maybe you push it like this. So here's the force of push that you apply to the door. So that's obviously one vector in the cross product. Mr. Hassman, can you tell me what the R vector represents in this torque definition? What is the vector R, Mr. Hassman?
It's like the distance away from the axis, but then it wasn't quite that. So
no, that's pretty good. So
it's just away from the axis is what I got from it. So.
Okay, yep, excellent. So this R vector is a vector that's drawn from the axis of rotation to the point of application of the force. Now, I hope you guys are noticing something that is different right away here. We're working towards using Newton's laws to analyze rotation. So when we've used Newton's laws before, the big one was this, right? Sigma F equals ma. And we may have looked at a force on an object in the x direction, a force on an object in the y direction to get the x and y accelerations, do vector addition to find the overall acceleration, et cetera, et cetera. But whenever we did this, we analyzed these objects using Newton's laws as just point particles, right? Like if I was looking at the door as a point particle, I would just draw it like this, where here's a pushing force going that way or something like that, right? So what we're doing now is we're saying that we can no longer represent objects when we're worried about rotation, when we're thinking about angular acceleration and how an object will change its rotational motion. We can no longer treat objects as point particles because the size and shape of the object now matters. The size and shape of the object will contribute to its I value, its rotational inertia, and where the force is with respect to the axis of rotation will contribute to torque. Torque is the rotational equivalent, the rotational analog, the analogy to force. Forces cause translational acceleration along a plane. Torque causes objects to rotate, to change their rotational motion, right? So torque is the rotational equivalent of a force. So we're going to do everything that we've done before. We're going to draw free body diagrams, draw all the forces acting on the object. We're going to sum up those things, but it's no longer just a simple force that we're worried about. It's torque, where torque is considering four things, I guess. Torque is considering how big the force is. So how big is this force vector? How far away are we from the axis of rotation? I said four things, maybe it's just three things. And then what angle is the force making with a line drawn from the axis of rotation to the point of application of the force? So yeah, let's talk about this R vector. Mr. Hassman said correctly that it is the distance from the axis of rotation to the point of application of the force, but it's a vector. It has a direction. So it's like a position vector almost, and it's always going to be drawn from the axis of rotation to the point of application, just like that. It is a vector that tells you how far away from the axis of rotation your force is being applied, okay? So the definition of torque then as R cross F is telling me to take the cross product of these two things. Of course, in a cross product, several things matter. The size of the vectors matter. The sizes of the vectors and the angle between the vectors matters. I recommended in the video that you redraw the two tail to tail like this, and then take the angle between them. But we did say that it works out if you just go ahead and take this angle here, because this angle is always going to be the complement. Like that angle shows up right here. Let me call this theta prime or something. And the sign of complementary angles is the same. Remember that we end up collapsing this down into RF sine theta. That's going to allow you to find the value, the size of the torque. Okay, so I really need you guys to understand conceptually the variables that is going to change torque. The bigger the R, the bigger the torque you're going to get. Now this is interesting. You guys can go test this right now if you have not already. I suggested that you go to your door, you open the door, and you just try to push it at different points. Maybe you push it here, you push it here, you push it here. Where is it going to be easier for you to cause the door to start rotating? The farther away from the hinges you are. That's the size of R, right? How far away you are from the axis of rotation. The farther you are away from the axis of rotation, the farther your force is, the farther your point of application of force is from the axis of rotation, the bigger torque you're going to get. And torque is what causes objects to rotate, right? So the easier it's going to be for you to set the object in rotational motion. So that R value matters. The size of your force matters, clearly. And then the sign of the angle between the two matters. So you guys need to understand that if I were to push this again with a new pushing force that may be pointed up this way, that's perfectly perpendicular, you can see, to this line drawn from the axis of rotation. The angle between them would be 90. The sine of 90 is 1. That's going to give me my maximum torque. Maximum torque occurs when the two forces are already perpendicular to each other. Remember, that's what the cross product cares about. The component of one that lies perpendicular to the other, right? However, if the angle gets smaller, like maybe now I apply a, oh boy. Maybe now I apply a new force. So let's call this F1, let's call this F2, and let's call this F3. It should be clear to everybody that F3 is going to supply the smallest torque, because the sine of that angle is going to be small, right? However, F1 is going to supply the largest torque, because that gives you the maximum sine value you can have. You guys all know that sine is between 0 and 1. The sine of 90 degrees is 1. The sine of 0 degrees is 0. So the closer we are to 90 degrees, the closer we are to perpendicular, the bigger our torque will be. So you need to understand that torque depends on all of these things, on how far away we are from the axis of rotation, the strength of our force, and what angle our force is making with that line drawn from the axis of rotation, right? Okay, now here's something we haven't talked about. A cross product is a vector product. It gives you a vector answer. That's not like a dot product. A dot product gives you a scalar answer. So torque is a vector. Who can help me understand in what direction torque points? Someone tell me what we do to figure that out. Ms. Thorpe, what do we do to figure out the direction that torque is pointing? Any thoughts?
Do we use the right hand rule?
We sure do. Yes, we do. Yay. The right hand rule. So this is, I know, kind of wacky for me to just explain to you in words on that video. So I wanted to go over it with you now. Let's get a new example here. Well, I'll use the same one. If you feel like you understand this really well, this may be frustrating for you to go over it all again, but hopefully it's worth your time. And we are about to work out some actual example problems you haven't seen yet. So, okay, so here's the axis of rotation. This is my door or something like that from a top view. And let's say that my force is this way. So here's my force of push or something. So first thing I'm going to do is draw my R vector like that. And you have two options. You can leave this alone. I am partial to redrawing them just like this. You do not have to do that. Okay, so to figure out what direction torque lies, the first thing that you have to realize is that, and this is true for all cross products, you guys will be doing more cross products in your future physics classes. Whoops. Okay, so whenever you see a cross product written, to figure out the direction that the answer vector, here in this case the torque vector, to figure out the direction it points in, you're always going to use the right hand rule. The right hand rule always works like this. You take your right hand, you rotate your wrist, align your hand so that your fingers are pointing in the direction of the first vector. So my first vector here is R. So I'm going to point my fingers, in this case, I'm pointing my fingers to the right, because that's the direction that R is pointing, okay? And then I curl those fingers of my right hand, I wrap them around so that they end up pointing in the direction that my next vector points, okay? So to do that, I'm going to have to turn my hand like this or like this, right? There's two ways right now for the fingers of my right hand to point to the right. They can be pointing this way with my palm down, or I can flip my wrist over and they can be pointing this way with my palm up. Clearly, to get my fingers to wrap around in the direction that the force vector is pointing, I'm going to have to curl my fingers in toward the left. So I need my palm to be facing up. I could not do that with my palm facing down, right? So my palm is facing up just like this. And what's important here is the direction that my thumb ends up pointing. If we do this, my thumb is pointing out towards me, out of the screen. So this is the wacky thing about cross products. The vector will always end up being perpendicular to, the answer will always end up being perpendicular to both of the vectors. So in this case, both of my vectors, force and that R vector, are along the plane of the screen or the piece of paper, if you're looking at a piece of paper. So how can you have something perpendicular to both of those? It must be on a different plane. It must be coming out of the screen or going into the screen, okay? So we can see here that torque is coming out of the screen, all right? Anything that's coming out of the screen, so I would say that my torque is pointed out of the screen or the page, coming out at me. We do have a way of representing that three-dimensionally. If something is going out of the page, it looks like an arrow coming towards you. So you draw a little circle with a dot in the middle. If it was going into the screen, it would look like an arrow tail going away from you, where here's the tail of the arrow like that. So it's coming out of the screen at me. And that is always represented as a positive value. So I would say I have a positive torque right now, all right? There's another reason why torque is considered positive in this case. It's because if I apply this pushing force this way, we all clearly understand that the door is gonna start rotating around like this. It's gonna have an angular acceleration like that. And that is, map that onto your unit circle. That's coordinated with the positive angle change on your unit circle, right? Remember that your unit circle starts at 0 right here and it goes around counterclockwise. So counterclockwise rotation is always considered positive. So I have a positive torque now that is causing that. All right, are there any questions about the right-hand rule or directionality of a cross product vector, about torque? This is important for you guys to know. Any questions? We'll be practicing it some more. Mrs. Spain has a question. Yes, what's up, Mrs. Spain?
Okay, so in the video you talked about there's one example where the torque wasn't coming in or out of the page, like it was actually on the paper.
Mm-hmm.
Okay, would you mind like explaining how that one was on the paper?
Yeah, not a problem at all. So I think in that example, well, let me just, we'll do one more example. That's an excellent question, Mrs. Spain. Okay, so let's say that, well, all we have to do really is kind of reorient ourselves. Let's say now that we're looking at like the front of the door. We're taking a front view of the door. Hold on, Mr. Bilek has a question. Which page of the review do I recommend that you print? Mr. Bilek, are you referring to the review?
I was just asking about the packet because 40 pages front and back would be a lot. We don't have a lot of paper in my house with 4 kids. So
Yeah, I understand. Let me think about that. I mean, I guess my recommendation would be not to print it at all. If you can like find some other paper to work on and just work from your screen.
yeah, I'll try that then.
What's it? It is 8:40. I think you should be working on the next thing. Yeah. Look at your schedule. Okay, so Mrs. Spain, back to your question. If we just now change our point of view and now maybe we're looking at the front of a door, it could be anything like the front of this pin, anything like that. And here's the axis of rotation now. Here's the hinges. And to get the door to swing like maybe into the screen or something, so that's kind of hard to draw, but imagine that this arrow is wrapping around the door to give it that angular acceleration. I'm going to obviously have to push on the door this way. So I'm going to actually now have a force vector. Let's say that my point of application is right here. I'm going to have a force vector that is going into the page. And so now my force is perpendicular to this plane, which means that my torque is going to end up being on the plane of the paper. Does that make sense? So Mrs. Spain, you're going to have a torque that is on the plane of your page or your screen when your force vector is the one that is coming into or going out of the screen. Does that make sense? So so let's think about this. So here's my R vector. From the axis of rotation, the hinges of the door, over to the point of application of the force. So if we do the right hand rule, I'm still going to point my fingers this way, but now I need my fingers of my right hand to be able to curl in toward the screen, which leaves my thumb pointing up. So my torque then would be pointing up along the positive axis of rotation. Does that help, Mrs. Spain?
Yes, thank you.
Yeah, great question. Yeah, so you can have times when your torque does point along the plane of the page, but in that case, you're going to have your force vector going in or out, perpendicular to the plane. Great question. Why is torque this way? Well, because as this thing rotates around, everything about it is changing except for one thing, the axis of rotation. So we like to define the torque vector in terms of either the positive or the negative axis of rotation. That would be another way of talking about it. This torque is going up along the axis of rotation, going up. So I could say another way of talking about it would be that the torque lies along the positive axis of rotation here. So that gives me the right hand rule. Okay. All right. So all of this ends up getting utilized with that definition of torque. If we're analyzing an object and it has different torques acting on it, we get Newton's second law for rotation. The sum of all the torques acting on the object is equal to I alpha. And this you guys must perfectly understand, and hopefully you recognize that it is the rotational equivalent of Newton's second law, where the sum of the forces equals m times acceleration. These are equivalent to each other, these are equivalent to each other, and these are equivalent to each other, right? Okay. Now, the complicated thing here is that whenever you sum up the torques, you have got to keep directionality in mind, right? So I think in one example, I had like a blobject, and I said that, I don't remember what I said, maybe that the axis of rotation was right here, and maybe that there was a force here. Well, you know what, I'll just make up an example. Maybe I have a force here going this way, and then I have another force right here that's going this way, like that. I don't think it's any, I don't think it's a complicated idea for you guys to understand that those forces are opposing each other. Force 1 is trying to cause the object to rotate counterclockwise. So I would call that a positive torque. And force 2 is trying to get it to rotate clockwise the other way. I would call that a negative torque. So those are opposing each other. So whenever you go to write your Newton's second law for rotation and you sum up the torques, you're going to have them in opposite directionality, right? So let's just do this. Let's say here's the axis of rotation. So here's my r vector. And then here's this r vector. Let's say this is theta 1. Let's say this is theta 2. And let's say that, I don't know, they're the same distance away, that the r's here have the same value. Then according to, according to Newton's second law for rotation, the sum of the torques equals I alpha. So let's say that maybe I wanted to figure out what the angular acceleration of this thing is going to be. Well, I just have to write torque expressions. So torque 1 due to this force is going to be F1 R sine of theta 1, right? That would be the size of the cross product of R and F1. And I want to count that as a positive value because once again, that force, that torque is trying to get the thing to rotate counterclockwise. Or if I do the right hand rule there, my thumb is pointing out of the screen at me, that's a positive torque, right? This one over here though, when I do my summation to add this torque, that's going to be F2R sine of theta 2. That is going to be in my equation as a negative value. So the directionality here is a little bit different. You know, in the past, when we have treated objects like point particles and collapsed the forces down there, we said that left was negative or down was negative or something like that. Here, the directionality is more complicated. You have to think about if the rotational acceleration that is going to be caused by the potential torque is clockwise or counterclockwise. This force is trying to get the thing to rotate around clockwise, and that's considered negative. So I need to subtract that away. You can also use the right hand rule for that. If I do the right hand rule for that left torque, I have to have my palm facing up so my fingers can curl around in the direction of F2, which has my thumb pointing into the screen, and that's considered a negative torque. So this would be my Newton's second law equation for this scenario. All right. Okay. So yeah, Newton's laws for rotation. Just like forces can cause translational acceleration, torques can cause rotational acceleration. All right. I don't know if you guys have had the chance to look through the packet that I've posted. Let me just go over a little bit that packet. So I'm about to share my screen with you to okay, can you all see the packet on my screen?
Yes.
Okay, yeah. Okay, so let me go over this a little bit. It's kind of a hodgepodge of all of this stuff. It starts with practicing the right hand rule, which I recommend you do. And then it starts to do there's all these pages about stuff rolling down inclines. Y'all can't do that yet. So I would ignore those pages. Ignore. You will be able to do them by the end of this week, and they're really fun. And then we get into some example problems using torque and things like that. This is where I would start looking if I were you. And some of these examples I did this example in the video. Let's see, this one has an object rolling, so you can't do that yet. Yeah, it's kind of all out of order, and I do apologize for that. This one would be a great one for you guys to look at. This is on page, whatever that is, page 50 or something like that. This one would be a really, really good thing for you all to look at. I wonder if we should do it now or if I should make you try it on your own. I think you should probably try it on your own. There is one thing that we haven't talked about here quite yet that is important for things like this. So here we have a pulley, and if you guys were watching the video carefully, in the past we've treated pulleys as frictionless and massless, right? But now we are thinking that the pulley itself has mass, and a pulley is a disc basically, so it has an I value. The rotational inertia of a disc is 1/2 mr squared. The pulley itself is going to rotate in the direction of acceleration of the system. So here in this example, this block is accelerating downward, which is going to cause the pulley to rotate around counterclockwise. Does that make sense? The only way that the pulley can be rotating like that is if there is a torque. So these pulley problems are really, really important that you guys are able to think through them and do them. So let me just go over some important things for that. So you guys should be seeing the whiteboard once again. I went over this several times in the video. So here's a pulley, and maybe here's a rope coming off of the pulley. Maybe it's anchored on this side or something like that. And here is a mass M. Well, the pulley itself now, I'm going to say, has a mass as well. Let me call this M1. Let me say that the pulley has mass M. Here's the axis of rotation of the pulley, and the pulley has radius R. As this mass descends, as the pulley like unspools, it has all this string wrapped around it. As it unspools and the mass descends, who can tell me where's the torque coming from to cause this pulley to rotate? The pulley is going to rotate as long as we are actually worried about it, as long as it's not a massless pulley. We have to think about the rotation of the pulley. So who can tell me what is causing the torque of that to rotate it? Mr. Davis, what could be causing the torque for this pulley to start rotating, to give it a rotational acceleration? Where's the torque coming from? If there's rotational acceleration, there has to be a torque somewhere. Any thoughts, Mr. Davis? You may phone a friend if you so desire. Mr. Bilek has raised his hand, so maybe Mr. Bilek can tell us. Yes.
Okay, I'll phone Mr. Mitchell.
Okay, Mr. Bilek, what's up, my guy?
Is it because gravity is pulling the other block down, so the force of tension is pulling it down?
Yeah, so it does come from the force of tension of the rope. That's excellent. So it's kind of unclear in my diagram, but this pulley is like anchored somehow by a support or something like that. So the pulley itself can't move up or down. However, it is free to rotate about this axis of rotation. And exactly right, Mr. Bilek, the force of gravity is accelerating this mass downward. And so this string here is taut. And I haven't drawn it very well, but right here, the string is interacting via friction with the pulley, with the edge of the pulley. So let me draw that a little bit more clearly. I apologize for my crappy drawing. Okay, here's the pulley. Here's where the string is coming off the pulley. This is much better. So right there, at where the string leaves the pulley, that is a point of application of a force, and it's going to end up being equivalent to the force of tension in this string, in this rope. All right. So think about Newton's third law. If gravity pulls down the mass pulls down the rope pulls up on the mass, and right here is where the rope is kind of supported, and it pulls down on the pulley. So if I wanted to analyze this scenario, I'm going to have to draw two different free body diagrams. A free body diagram for the mass 1, where I have force of gravity, which is M1 little g, and then a tension force from the rope. And then I need a free body diagram for the pulley, and it's going to have to be sometimes what I refer to as an extended free body diagram, a free body diagram where I actually show the shape of the thing. And the force acting on it that I'm worried about, again, yeah, gravity's pulling it down, but there's something to support it to keep the pulley from falling or something. This force here, as Mr. Bilak said correctly, is the force of tension as well. So these two are equal to each other. Does that make sense to everybody? This force of tension is located some distance r, the radius of the pulley, away from the axis of rotation of the pulley. So it meets the criteria to supply a torque to cause the pulley to rotate around like this. All right. So I can now write Newton's equations for these two objects. This is mass 1. This is the pulley. So Newton's second law for this, remember we always want the direction of acceleration to be positive. So I want down here to be positive. So Newton's second law for this scenario would be M1G minus force of tension is going to equal M1A. And can someone give me, oh, Mr. New, can you give me the Newton's second law equation I'm going to write for the pulley? It's going to be in this form, right? So can you expand that for me, Mr. New?
Expand that. Let's see here.
Yeah, like what is my torque? What could I write for torque for the pulley?
No idea.
You want to phone a friend?
I don't know who would know.
How about Mr. Coleman? I bet he knows. Give me an expression for the torque on this pulley.
It says here torque is the cross product of R and F.
Correct.
So R would be the big R.
Correct.
And would our force be the force of tension?
Exactly correct. Yeah. And then cross product is worried about the sine of the angle between those two things. So what's the angle between R and F?
That's 90. And the sine of 90 is 1.
Excellent.
So it would just be RF?
Exactly correct. Yep. That's the torque. RFT. Very, very good.
Interesting.
Yeah. Perfect explication, Mr. New. That's exactly how you guys should think through it. Torque is R cross F. So here's my R vector. It's a vector drawn from the axis of rotation to the point of application of the force. Here's my force. And of course, those are already perfectly perpendicular. So I don't really care about the sine of the angle. The sine of 90 is 1. Yep, just like that. And that's the only torque acting, right? That's the only force that is away from the axis of rotation. So I have no other torques. That's the sum of my torque. And that is going to be equal to I alpha. All right. So the problem is now I want to try to get these two equations to speak the same language, so to speak. I want them to be able to coordinate so I can make like a system of equations. The problem is that I have an alpha in here, and I have a linear translational acceleration in here. Miss Brooks Scott, do you have any thoughts about how we can modify one of these equations to get them to speak the same language? What could I do to the alpha, maybe? Any thoughts? Miss Scott, Miss Brooks Scott, let me ask you this question, okay? So listen carefully. The mass here is accelerating downward due to the net force supplied by gravity. Is that correct?
Yeah.
Okay, excellent. And the mass is connected to a taut, tight rope. So every point along the rope is also accelerating down with that same acceleration. Is that correct?
Yeah.
So a point right here on the edge of the pulley wheel must also be accelerating with that same acceleration. Is that correct?
Yeah.
So it seems like as long as the rope is not slipping over the pulley, as long as the rope remains taut and doesn't like slip over the pulley, As long as the pulley and the rope kind of stay together and rotate and move together, then this acceleration that shows up in this equation can also be thought of as a tangential acceleration of this edge point on the pulley. Is that correct?
Yeah.
Okay, so everyone should remember that for objects kind of moving in a circle, we can think about tangential quantities. So this thing is rotating, and it's speeding up as it rotates. So I have these tangential accelerations that are pointing like this. You guys remember this? So Ms. Scott, it seems like what you have just discovered is that the acceleration of the mass is the tangential acceleration of the whole system. That is the acceleration of this point on the pulley edge right here, and it's a tangential acceleration, and those two are equal, correct?
Yeah.
Yes, okay. So do we have any concept or equation that can relate that can relate rotational quantities and tangential translational quantities? Do we have an equation that can help us do that? And do you know it, I guess, is my question.
I'm looking.
Okay.
I don't know.
If anyone else thinks they can get it first, feel free to beat out Miss Scott. Although she's doing such a good job. Thank you, Miss Scott. Anybody finding it? Mr. Bilak has found it, maybe. Yes. Go for it, my friend.
I have in my notes the tangential acceleration is equal to the rotational acceleration times the radius.
Excellent. Very, very good. All right. This is not on your AP equation sheet, and you guys must absolutely know these relationships. This is the pattern of the equation that gets us from translational tangential accelerations or tangential quantities of any kind. It could be velocity, it could be acceleration of a point on a rotating object. It translates the tangential translational quantities and the angular rotational quantities. For example, it all comes from this. You guys need to know this. It's just geometry. Here's a circular object, and let's say that I'm looking at a point on the object right here, and that point moves. The object rotates, and that point moves to right here. So I can talk about how that is, if this is the center, I can talk about how that motion was an angular motion, like this point swept out an angle theta. But I can also talk about the actual length it traveled, where that's just an arc length. So the arc length equation says that, hey, the length S of this arc is equal to the radius times theta. If I take the time derivative of both of these things, then I'm going to get speed or velocity, the arc length, the distance, the displacement traveled per time would be velocity, and that is a tangential velocity. And I take the time derivative of theta, and that's omega. Maybe it's speeding up as it does this. Take the time derivative again, you'll get tangential acceleration equals r times alpha. So these equations, you guys must know them. It is how we get from the translational tangential world to the rotational angular world, all right? And the key realization in problems like this, we'll talk more about this later. In fact, I'm going to post a video later today for you all to watch tomorrow. This is only true if we say the object is not slipping. So in other words, as this rope unspools from the pulley turns and the rope is accelerating, and they're kind of doing that together. The rope is not getting ahead of the pulley is not like skidding on the rope, they go together. So they're not slipping. Therefore, the acceleration of every point of the rope is going to be the acceleration of that edge of the pulley, which is a tangential acceleration. So that is this acceleration that shows up in this Newton's second law equation that we've written for the box. It's also the tangential acceleration of the pulley edge. And so if I know what, if I write this Newton's second law equation for rotation and get an alpha, I can rearrange it using this, which is always true as long as as the two things are not slipping past each other, as long as the rope is not slipping or skidding on the pulley. I can rearrange this and say that, hey, my alpha is going to be equal to A over R. I can plug that in here, and now I have two equations that speak the same language. So this equation becomes RFT equals I times A over R. And of course, we have to think about what the I value is. If this is a disk, the I for a disk is 1/2 mr squared, et cetera, et cetera. Now we can, maybe combine these equations and solve for acceleration or solve for the force of tension if we know the acceleration, something like that. And of course, if we solve for the acceleration, we'll be able to plug it back in here and get the alpha. So this is the key realization, is that we can make our two equations speak the same language by understanding these rotational and translational relationships. And that's always going to be a key part of solving these problems. So let's talk about the problem-solving strategy here. The problem-solving strategy is just what we've always been doing with forces and acceleration. Draw free body diagrams, write Newton's second law equations, make the direction of acceleration your positive direction. The only thing that we're changing really is that now we're saying, hey, some objects could be rotating. And if they're rotating, we're going to have to actually treat them as extended objects that have shape. Think about where the force is, because that's going to change our torque expression. And then write a Newton's second law equation for that. Any torque that is contributing to the rotation is going to be positive. Any torque that is trying to rotate the other way is going to be negative. And then we make the two equations, as long as we don't have slippage, we make the two equations speak the same language by using this relationship. And then we could solve for whatever we wanted to solve for here. All right. So generally speaking, that's going to be how we're going to solve these torque rotation problems, generally speaking. All right. Are there any questions? Ms. Thorpe, yes.
Could you use the equation for tangential and acceleration and plug it into the equation we found for mass 1 and solve for alpha that way, and then plug it back into
So you're saying take this and plug in R alpha?
Yeah.
Yep, you could definitely do that for sure. Definitely.
Thank you.
Yep, good question. Yeah, whatever algebraic tricks you need to pull to do that, to solve. It just depends on what the question's asking you for, I guess. But yeah, excellent. Anything else? I know I've just kind of recapitulated the video that most of you have already watched, so hopefully, though, this was helpful. Hopefully you gained some clarity. I was thinking that I would work some example problems, but really the only ones I have right now are the ones from the packet, and I kind of want you guys to give that a try. So let me pull up the packet on my screen, if that is okay. So if you guys could, I know that the page numbers in the top corner of the packet are not super great. Some of them don't show up, but if you can kind of go through and find any problems that deal with torque, any problems that don't have objects rolling down inclines, basically you guys are able to do. This would be a really great one to do here on page 13 of the PDF. There was another one past this. Yeah, this one would be an awesome one for you guys to do. This is page 16 of the PDF. It's also page 54 of the packet. I know the numbering is wacky. This one would be really, really good for you all to do. Ooh, this one is really challenging, but it's really fun. Page 17 of the packet. This one would be good. Page 57 or page 19 of the PDF. You guys could do this one. This would be a great one. This is an old free response question, page 21 of the packet. So why don't you guys take the rest of today to work on some of these homework problems in the packet, all right? And then next time that we meet together, we can go over some of them. I'll work some of them out, but I really like for you guys to give it a try on your own first, all right? So let me think about what I was planning. I have the next videos ready to go, which the videos are all about objects rolling along surfaces. Really important types of questions where we look at how objects roll along flat surface or along inclined surfaces like this. But I'm thinking maybe you guys need some more practice with regular torque stuff before we do that. Okay, so listen carefully. I'm going to type this up on the Google Classroom as well, so we all make sure that we get it. If you guys have already tried some of these torque problems, and if you feel like you're comfortable with torque and you're ready to go, for example, if you can do this one here on page 13, if you feel like you can do this one here on page 16, if you do those, this one here on page 21, if you do those and you're feeling confident, then you can go ahead and continue on with the video I'm going to post today. I'm going to post 2 videos for you guys to watch and take notes over about rolling, as I've said. If not, just practice these problems. And I'll have a deadline maybe of Friday no, not Friday. I don't know. I need some time to figure it out. Anyway, here's my plan. I'm going to give you guys the rest of today. This will be some homework you have to work on today. Tomorrow as well actually, I take back what I said earlier. I'm so sorry. I'm going to give you the rest of today. I'm going to give you tomorrow to work on this packet, work on the questions I've suggested. And then also, yeah, I would like for you guys to go ahead and take notes over the new videos I'm going to post. And then here's what we'll do on Friday. On Friday, we will go over, I'll work out for you some of these practice problems that I've suggested that you look at. I'll work them out for you in class. And then I will also take any questions that you have over the new videos. On Monday, we'll have it. So our next Zoom meeting will be Friday. On Friday, we're going to go over some of these practice problems, also go over briefly the new videos I'm going to post. So 2 things that you need to be working on, this packet and the next video I'm going to post. You have until Friday morning to do all of that. It's plenty of time. Friday, we'll go over all of that. And then our next Zoom meeting will be Friday, and then we'll have one again on Monday. And then at that point, we should be mostly done with rotation. So on Monday, we'll be going over some more problems, and there is a lab that we need to do that you guys can actually do in your homes. I think I mentioned it earlier that probably we won't get to until sometime next week. So right now, the plan is for you all to work on this packet, be on the lookout for the new videos I'm going to post for you to watch and take notes over. And then we'll meet back on Friday to go over these practice problems and to talk about the new video. Does that sound okay to everybody? All right. Any big questions or comments or cries of outrage that anyone has? Are you guys feeling okay about the format of me posting new content as YouTube videos and then us discussing them? Is that working out for people?
Yeah.
Was that a yes? Yes, okay. All right, so I think that's just what we're going to keep doing. You know, we're almost done with the stuff that will be on the AP exam. This rotation unit is the last thing that's going to show up on the AP test. So they're supposed to get those dates. Can I post the recommended problems for the packet on the classroom? Excellent idea, Mr. Davis. I sure will. They're supposed to get us the possible dates for the AP exam by Friday, so I'm not sure. Mr. Nandy has a question about the AP test. Yes, what's up, Mr. Nandy?
So apparently AP tests are going to be open book now. And so I was wondering about like how that would affect us, or I don't know.
Well, so I don't quite know what they're going to do for test security. You know, I'm assuming that there's no way for them to make sure that you don't have access to notes and things. Here's my thinking about that, Mr. Nandy, and I'm really not sure. You're going to have 45 minutes to answer some free response questions. I'm anticipating that they're going to make it really difficult for you to be able to sufficiently answer the questions while like flipping through your notes. Does that make sense? It's just going to take too much time for you to like worry about your notes and stuff like that. So I don't know. While theoretically, technically speaking, you could have materials there, I think they're going to make it so that if you spend time doing that, it's going to be to your disadvantage. Does that make sense?
Yeah, the only reason I was asking is because I think like the head of AP testing like released it on his Twitter or something that it was going to like they were going to make the format open book, but I have no idea. So,
okay. Well,
I saw that tweet.
Man, I gotta get myself on Twitter apparently.
On the PDF online and use Control F.
They're supposed to be the head of AP is supposed to be releasing like some kind of update either I think tomorrow or Friday. So I'll have more information as exactly of what they're going to expect from you guys hopefully by next week. Okay. Mrs. Spain asked if she wanted to review this video. Where can she find it? I'll be uploading it to the YouTubes. So on my YouTube channel, it's just my Haas account. I have playlists. I have a playlist for this class, AP Physics Mechanics. It'll be there. I'll also post it to the classroom. All right. Okay, guys, thank you so much for your time. I hope you all are feeling well and staying healthy. It's supposed to be another pretty day, so get out and enjoy the sunshine. Don't forget, you do have an assignment due tonight, and it is to tell me how you enjoyed some sunshine, okay? Thank you guys for your time. I appreciate you all being patient with me as I try to figure out this whole Zoom class of 2020 thing. Yeah, so you guys know that you need to be working on these practice problems and be looking out for the next video I'll be posting on the YouTubes. All right. If you guys have any questions or comments or problems at all, please feel free to email me or reach out. All right. And if I don't hear from you before then, I will see you all back here on Friday morning. Okay. Thank you guys.